Okay, so we're going to, in this video, compare confidence intervals for the normal and for the t-distribution. And so we're going to take a very highly skewed sample. The sample size is 50, so because it's greater than 30, central limit theorem will apply. Thus, the distribution of sample means, by the way, remember it's not the individual scores, it's sample means is approximately normal for each confidence level. So we can go ahead and proceed with the normal here. We could also proceed with the t-distribution. This time we're telling us the standard deviation of the population is known, and which means that because the standard deviation is known, we can use z-scores, we can use the normal. And the formula for the confidence interval where sigma is known as follows. Well, x bar plus or minus z star standard deviation divided by the square root of n. Well, we have a sample mean, some sample mean, plus or minus, we'll get to what our z star is. I gave you the z star value of 1.645. I'll tell you where that is in a moment. Our population standard deviation divided by our square root of our sample size, which happens to be 50. All right. Well, this is z star. We're going to do a 90% confidence interval. All right. So basically, if we want a 90% confidence interval, the z stars associated with that is 1.645. So let me tell you how to do that. You're going to need to use your calculator. And we're going to go to second bar's inverse norm. Our area, when it asks for area, is going to be 1 minus our confidence level, or in this case, 1 minus 0.90 divided by 2, with a mean of 0, a standard deviation of 1. So we'll go ahead and run that off real quickly. So second var's inverse norm, areas, parenthesis 1 minus 0.90, close parenthesis, divided by 2, mean of 0, standard deviation of 1. And I end up getting negative 1.645. All right, so that's where that comes from. So plus or minus 1.645 is our z star. Now, our population standard deviation is known, and so it's not going to vary. So all of our interval widths are going to be the same. Okay, now when we do a confidence interval, if this line represents my true population mean, so this represents my true population mean, these intervals are going to sometimes capture the mean, and sometimes it won't. Sometimes they'll capture really close to the sample mean, because the dot will represent the sample mean, and this would be 90% distance. Well, this one caught it, this one didn't. And then caught it. So we're looking at these, and these caught it. Then also we have another one over here that didn't. And this is showing two. This is showing 2 that didn't catch it out of 20, which basically 2 out of 20, which means 18 out of 20 did capture it, which is 90%. And really what we're saying is, if we do a confidence interval enough times, if we do it over and over again, 90% of the time, it'll capture it. So 90% of the time, this would capture, but please notice, because we know our standard deviation of our population, the widths are going to be the same. The middle will always be the x bar. So the x bar is my best estimate, and this time it just was wrong, because every now and then the sample won't match. When we go to the t-distribution, and by the way, I'm still keeping the sample size 50, therefore the distribution of sample mean says it's normal by central limit theorem. So I can still go ahead and do that, but when we go to the t-distribution, we're having to use the standard deviation of the sample, which means every time I take a sample, I'm going to have a different standard deviation. So all of my interval widths are going to vary. Some are going to be narrower, some are going to be wider, depending on what sample I have. All right, I still wanted to do a 90% confidence interval. And to do that, I'm going to have to go to a slightly different place on the calculator. So this is going to be a second var's number 4 inverse t, 1 minus my confidence level, which happens to be 90% this time. And then, and divide that by 2. then it's going to ask me not for a mean or standard deviation, it's asking me for my degrees of freedom, which is my sample size minus 1. In this case, 50 minus 1 is 49. So second bars, inverse t, my area, parenthesis 1 minus 0.90, close parenthesis, divided by 2, degrees of freedom, 50 minus 1, or 49. And I end up getting 1.676. All right, so 1.677, and when we worked with a normal, it was 1.645. So notice I'm a little bit farther spread out. Why? There's more area in the tails with the t distribution. So when I look at this, again, this line represents the true population mean, and I expect my confidence level interval to capture it 90% of the time. So this a little bit wider, narrow, but so far we're capturing it. And then we have this one here, number 6, that does not capture it. We have a number 10 that doesn't capture it, but still 18 out of 20 times we capture the true population mean. And that's about 90% of the time. In reality, 20 times is not enough. We're going to need to do it a bunch more than that. But what we're going to say is we are 95% confident that the true population mean lies within an interval, or if we did this over and over again, which is what we're doing here, if we did an infinite number of times, 90% of our intervals would capture it, okay? All right, so hopefully that will help with the understanding of the difference between the normal and the z, the normal and the t distribution. Once again, this is 1.67 versus a 1.645 for the normal. All right, thank you.